Just a couple of quick announcements. We're gonna have a meeting in a couple of weeks. We'll send out an email about the actual time for it, but just to all get together and just have an even more social meeting than the presentations. So that'll be coming in the email. Also, want to make some announcements about upcoming speakers. Our next meeting, our main meeting, will be featuring Dr. Barry Trimmer, who's going to talk about robots made out of soft materials. Okay. All right. Yeah, cute little caterpillar. Did we bring a video this time?
I think he has a real video camera, but I have the. I was gonna do it with this. I don't know. Is yours?
Will that work?
Oh, okay. I'll do it with this, and it'll be low resolution, but the sound will be there, so it should work. It might work.
Embryogenesis, about how you get one cell to grow into 250 cell blasts. Focusing on how the cells learn behavior through that.
Wow.
Oh, no, the
So
sound.
without any further ado, Paul.
Well, just a slurping in the background.
It is a permanent thing.
Can I do it?
Oh my God, there's so many things on it, I can't tell what it's doing.
Okay. I've been coming to these talks since the beginning, and I've been very excited by all the various things that are presented and by the work that people have been able to do. And when I contemplate this, I get nervous because it seems like intelligence is a lot to shoot for, and when I try to think about algorithms in order to evolve things, I come up with very little algorithms, things that would do very small things. So I'm doing a simulation that's going to try to do some small things and hopefully get some accomplishment. The various sorts of life systems I've seen presented typically are of two categories. One is they don't do anything interesting, and the other is that they cheat in some way. By cheating, I mean they're not built out of one thing, they're not built out of one type of thing, or they have instructions that say things like, reproduce myself, which is this very high-scale capability, when the rest of the instructions are things like if and loop and so forth. So I'm going to try to do something at the very bottom and see if I can do it kind of honestly. Do I expect to get magical results? I don't know. We'll see. Anyway, the reason why it's called this is the reason why the problem daunts me is it's got so many zeros in it. When you're up in this domain, there isn't much to think about except the zeros. And the main source of zeros is Mr. Avogadro, who provides us 23, which goes from the molecule size, where evolution happens, to about the size of a sugar cube. And then, of course, in the oceans, you've got a lot of sugar cubes. So, the questions I'm interested in answering, and the simulation that I've created to attempt to address those, are what should we be doing in the artificial life area? What can we do? In other words, will it be the case that we can never do certain things? And how much computation do we have to wait for until various things become feasible? The wild card in this is, what does intelligence buy you? Because sometimes intelligence buys you quite a lot, and sometimes it doesn't get you anything. Then we're discussing the question of what it means for a system to evolve, and can we tell it's evolving? What's the sort of metric we use to tell? And then finally, of course, well, what do we want that for anyways? Now, all my high tech has failed to materialize. I had a tablet to scribble on things, but that won't be happening. I appear to be crooked, and my automation isn't working, so basically it's like evolution. Okay, so the inspirations for this work, and maybe for a lot of you, the first one is, I don't know, the first program I wrote when I got my hands on a computer said, what is your name? And it took your name and it said, hello, whoever you are, and that was very exciting to me. The computer was talking back. Now, you get to the point where you want more of that, and that's no longer sufficient. You want the computer to do more interesting things, and so now we want to evolve things that will talk back to us. Maybe figure out our name without asking for it.
My program's like the whole world.
Exactly. I'm not a world, though. Okay, the inspiration for the particular level I'm doing is the famous Miller-Urey experiment, which we probably all ran into in high school, which is they created the primordial soup, they ran it for a week to see what they'd get. Now, I don't know about you, but I was hoping that the next thing the professor would say is something crawled out of it. And what they got was the precursors of life. And I said, that's it? They got the precursors of life. They got a couple of amino acids in it. And I realized that if they could have only run the thing for another 100 million years, something might have crawled out of it. And so I remember thinking, all right, how long do we have to wait before computers can make that thing run for 100 million years? And that's the inspiration for the molecular simulations that I'm doing currently. I had a nice little button that went to the next frame, but it escaped. A general point that people mention in the field is AM and Eurisco. Who knows these things? Hands? Okay. You run into these in AI classes as a demonstration of something. AM was a program that Doug Lennett wrote in '76, which found interesting facts about mathematics. So you gave it basic things like there are objects and sets of objects, and then it would discover things like there are some sets of objects that can't be divided into smaller sets of objects, and you can call that primes and so forth. And so AM sat there and chugged along, and after a few weeks, it in fact did discover the concept of primes. Wow, that's pretty impressive. And then if you ran it again, it discovered the concept of primes. And no matter what random source or what sort of information you put into it, you could get primes, but you couldn't get much further than that. It seems, and Leonard agrees, that it's kind of a predestined learning here. He was trying to get a system that had basic elements to go up and be clever, but it was more like an arrow that was aimed at a target. And once it got there, it didn't go much beyond that. He generalized AM into Eurisco, which isn't about mathematics, it's about anything. And Eurisco has been applied to designing chips, it's been applied to other things, and it's had a fair success at it. So I'm claiming that it's not very deep. What am I claiming it is? Oh, I think it's a really, really good hill climber. It's an optimization system. You give it a set of stuff, and it finds the optimal set of machinery. But when we talk about evolution, I think we talk about more than just climbing up a hill. Because normally, we expect that something gets optimized, and then somebody discovers something much better, and that optimized thing loses out to it. And maybe if you could have ran this for 100 million years, it would optimize as well to a deeper level, but it didn't seem to. Okay, and then we have the Core War classes, which started out with a game called Core War. Who's familiar with some of these? Okay. And again, I read the Scientific American column, and I excitedly went and implemented that sucker. And the idea that little programs could fight each other seemed obvious and would definitely work. And I don't know, who else implemented this? Okay, well, you get 6 different creatures when you set it in evolving. They're the same 6 that other people have gotten, and then you discover the one that just runs which is 2 instructions along and runs all over everything and kills it. So you try altering the parameters, and you try moving it around, same 6 creatures, and then dead. A system that followed on that, or was based on that kind of concept, was Sierra by Tom Ray, and then a system that was based on that was Evita by Opria and others. And there they are, and the final one has broken into 2 dimensions. However, I'm afraid, I don't know, anybody know how many creatures Evita gets before something kills it all?
It varies, but it does eventually reach a stable state.
Right, and my complaint would be it reaches a stable state in my lifetime, which means that it can't be doing all that much evolving, since I should be able to keep it running and see all kinds of weird things going on in it. So all of these, I think, are still doing some kind of optimization. And Evita in particular have to do all kinds of patches for anything that kills it. So anytime they come across something that kills it, they put in a new sort of feature, like, the creatures have protected memory, so the one that runs over everything can't run over you anymore. But the question is, what's the physics model of all this, right? You started out with some programming instructions, and now you're protecting those programming instructions, and there's no unifying shape to it all. There's just an attempt to patch things. And then finally, what inspired the particular kind of...
Won't PG down and PG up do it?
What?
Won't PG down and PG up
Not
do
in
frames?
Photoshop, they won't.
Oh. Photoshop.
Yes, it's Photoshop so that I can scribble on it with my tablet. Sorry about this. Nope. And the final inspiration was, again, that I lose sleep at nights thinking about the size of 23 zeros. I just can't imagine that anything that evolution manages that I can do in my scale in my lifetime with the machinery that I've got. So, to paraphrase Mr. Adams, infinity is really big, and even sufficiently large is nearly as bad. And that's why all that matters is counting zeros. Okay? And so when you're going to do a programming task, you count up how many you need and how many you've got. Well, time is 10 zeros, that's about 1 billion, which is the evolutionary time scale. The planet has about 20.
But you're talking years? Why not talk about a small time scale, like chemical reactions go?
Okay, I'll give you 3 more.
No, it's more like...
Well, actually, if you're talking about things on the quantum mechanical level, you should be talking nanoseconds or picoseconds.
Right.
Yeah.
So that would add like another 15, say.
Yeah.
And that'll depend on what we decide a reaction is, right? So I'm perfectly happy to throw in another 4 or 5. The fun with playing with zeros is it really doesn't matter. In the shadow of Avogadro, that number there is going to go from 53 to 59, and I really don't care. Anyway, besides, the planet, that's only counting things down to the size of a sugar cube, and then to go from a sugar cube to molecules, we get Avogadro again. So that's 53, 4 more, as you say. And the question is, how many do we have? Well, I don't know if anybody made sense of that equation in the abstract. Take the current year and subtract 1960, divide that by 5, and that gives you the number of zeros of computation you've got. Basically, that's Moore's law on base 10. So that would be 1 billion. And if you think about that, that would say in 2010 we'll have 10 billion, which would be 10 gigahertz, which we approximately expect to have. Now, of course, hertz, as you know, as you would say, is not instructions, and that's not operations, so you might have to knock a 0 or 2 off that. The point is that if you subtract one of those from the other, you're not going to be simulating the planet anytime soon. However, you don't have to if you're clever. You also add in the zeros for how well you engineer the system. Engineering is taking advantage of coherencies and things like that because you have insight. Okay, so mathematics gives you insight, and then the smarts that you yourself, the programmer, put on top of it gives you insight. And mathematics gives you one question mark, and smarts gives you an arbitrary number. And so the original question for this talk is, in this domain, how many zeros does smarts get you? My system hopefully will allow you to experiment with that. As an example of what smarts gets you, suppose you wanted to compute n factorial, n times n minus 1 times n minus 2. What's the order of the algorithm? It's order n. There's a cheaper algorithm for it. What is it? Well, there's a closed form somebody figured out. There's just a formula. So that takes it down from order n to 0 time for computation. So sometimes humans just cross out all the zeros if you're smart enough. So hopefully we're hoping to end up somewhere between 53 minus 9 and 0. All right, so let's be engineers. Clearly we need an evolutionary system to be Turing equivalent because evolution evolved us, and we're certainly Turing equivalent. What is Turing equivalent? If you have a computer with no data, is that Turing equivalent? No, that's called a finite state machine. If you have a computer with a limited store, is that Turing equivalent? Well, it could have a finite sized tape, but if it does have a finite sized tape, then really it's just a finite state machine with a heck of a lot of states. A computer with an infinite store? Yes, that's Turing equivalent. However, a system which just has a blank tape to start out with, no matter how big it is, contains only a finite amount of information. Can it continue to innovate? No. It's only got what it's got. So, what's odd about this is even an infinite computer probably can't do evolution in the way we want it to. It needs a whole bunch of random input. So it needs some kind of random number generator or a tape that's already full of some noise. Wagner recently and others have started to talk about a concept of evolution equivalence, which is similar to Turing, but for creatures that for things that emerge. Turing equivalence is not enough. You also need a system that realizes that in some form where there are objects which move against each other and can emerge. So, what do we really want? We want to see something new in a system that didn't contain it. That's where I think Corwar and Eurisco fall down. I think those systems generated something that we thought was new, but because it was hidden in there, right? It was basically a thing that was behind a curtain, and then we revealed the curtain. And then the question is, what's new? Okay, to answer the question of what new is, this is my bold and unsupported claim for the fate of all evolutionary simulations that any of us will ever do. Okay? And this gets back to the point of, well, okay, you get an initial set of chaos, which is based on the initial conditions you put into the thing. Suppose you filled your your model full of sugar, then you're going to get some chaos until it's all eaten up. But then, out of that, you're going to get some opportunistic creatures who are figuring out niches and are evolving themselves into more complex patterns and are making more complex systems and becoming more interesting. And then at some point, everybody's going to have figured out all their niches and all their strategies, and you're going to get a flattening off period when basically you'll continue to get creatures which will eat other creatures in new patterns, but they won't be a level of complexity above what we've already seen. Basically, if you got fish, you'll get more interesting kinds of fish. You won't get double colorful fish, you won't get schools full of fish, and so forth. That's because that level is implementing some level of particles. So fish could be a level of particles. If you wait long enough, and the system's big enough, something will get implemented on top of the fish, because the fish then become particles and they have behavior. Okay? So if you waited long enough, a quantum level longer, you'd see an initial chaos, and then an evolution, which is using fish as its basis, and which goes up. In ourselves, you can make the example that you're full of cells. The cells that you're full of don't in fact have a thought that they're part of you, and that they all group together. What they do know is that they're in a very hospitable and rich environment, because cells grouping together into one of you is a much better strategy than a cell by itself. So, the cells are all happy, they're down here, and they're still operating. But what you're seeing move up is the thing that's built out of the cells, that come up with animals or something like that. The problem is, if you're looking at the cell level, and if your visual tools are looking at the cells, you will never notice that something got built out of them. So it's important to keep track that your visualization tools don't evolve. So the system may be evolving, and you may not know something new when you see it. It might be some sort of meta pattern. At any rate. So, as an example of this, you start out with atoms, they build into interesting molecules, molecules built into interesting machines, the machines build into interesting cells, and the cells build into interesting animals. And each one of those, I would claim, is another quantum level longer that you have to watch the sort of things go on. Now, what will happen eventually? Will this just go on forever? If the universe is infinite, yeah, I think it will. But the universe isn't. And at some point, you won't have enough particles of whatever level you've gotten up to implement something interesting on top of it. For example, are we going to get something built on top of humans? I don't know. 1 billion of them just doesn't strike me as very many. We've got more than 1 billion particles in a cell, you know. So it seems unlikely to me that I think animals are it as far as just one planet is concerned. In the entire universe, there might not even be enough planets to implement something on top of that, assuming physics had some way of doing that. So I would claim that all systems level off to a final equilibrium, a final that's nice sort of thing, when they run into their limit. And my argument is, the limit of most of the systems we've been doing is this one. No interesting levels. Okay? If you can only put in 1 billion particles into your system, and you don't tweak it, then that may not be enough to get you a level, unless you do some engineering cleverness. It's interesting to note, by the way, that the eventual fate of this, by the way, is back to 0. Why? Because this thing will have some wobbles in it, and the wobbles can go up as high as they want, but if the wobble ever hits the baseline, right, like in that particular generation, you know, it's very rare, but nobody had any offspring, the system is dead and will never come back again. Or it could start taking off like this if it's got energy again. So,
Usually how, like, one dimension of this looks, just because, you know, evolution happens over the entire surface of the planet, and so it's more like 2 or 3 dimensional, you know, all these things going on. There's all kinds of localized effects.
it's more like 40 dimensional. So what we're looking at is some arbitrary graph of complexity, some arbitrary metric that measures from 0 into very evolved, and whatever that happens to be, I'm claiming that this is kind of the profile for it.
Well, there's actually 2 things. One is you made a really good point when you were talking about, you know, for example, you look at a system like a Vita. You know, they've run a Vita on giant clusters of computers. We don't know that extra levels aren't evolving on top of the cells because we have no idea how to detect that.
That's true.
The second thing is we don't really know how to quantify evolutionary innovation. That's a related question.
Yes.
The only thing that I've ever been able to do with the systems that I work with is looking at what's called compressibility, which is basically a measure of redundancy in data, which is you just run the data through a compression algorithm and you get a relative measure of redundancy. And what you see there is, you know, sort of an adaptation curve. But that doesn't tell you much about how many levels are going on in there.
What your first statement was that, you know, these systems might have things evolving higher levels that we can't detect, and then your second statement was that looking at compressibility, you actually can detect when the information is there. You may not know what it means.
You don't know what it means.
We're arguing that
it
might not be a good metric.
Yeah, I don't think compressibility is that good of a metric. I think it just tells you information content. It doesn't tell you levels or...
No, it doesn't, but it would definitely be able to tell you the difference between being here and being here.
Yeah, it can. It can tell you that something happened.
Right.
Well, that leads into the next point here, which is what kind of things do you want to look for, given that you won't be able to write an essay on what you see? Well, the particular thing that kind of we think of as life-like or intelligence-based is a discontinuity happens. You're getting something nice and smooth, and then you get a race up. Or, if you look at the geological record for when humans show up, something was happening, and then there's this bizarre spike, and who knows what will come up after that, but it won't look like this. So, if you were looking in the record, you'd see a sudden discontinuity, which says, oh, that was an intelligence line there. Something popped up and happened in very fast time.
I thought there was a pretty good graph on body mass and intelligence for most creatures, with 2 exceptions off of that graph. It's like a power to the 2/3 law or something like that. The 2 exceptions being humans and dolphins that go off of that line. But there is a kind of...
Well, let's talk about the different innovations that might be considered on this one. Okay? Everyone agreeing on left-handed amino acids. That, I think, was a fairly big one. Everyone agreeing on DNA, that was really big. The discovery of chlorophyll, that's probably one of the last ones. The invention of cells, yeah, that's pretty good. Animals, I'm less impressed by animals than cells. But this whole system you're talking about is in the animal domain, a very small territory. Once cells decided to group up, I would say, you know, the daily newspaper for molecules wasn't impressed after that by what happened. We are. But as far as evolutionary strategies are concerned, those are all very short term. We'll have to see if they're generally viable. The only one of the animals that I think would get column space is insects. They're very viable and very long term and very diverse.
I think there were actually a lot more things than that, but a lot of them are more specific and more subtle. One example would be for meiosis. Meiosis.
Sexual reproduction.
That's right.
That there are actually big evolutionary advantages.
I would love to get together with a bunch of people and make the hit list that the bacteria would have read about, you know, on their newspaper, because it would give us some perspective.
Inventions of evolution.
Inventions of evolution, and I want to put, you know, all of animal kind in
I Googled for that title, and because I wanted to read it, but no one's written it yet.
off in the corner.
I have a question.
Yeah?
You said that animals or humans were kind of the top of the chain, but I've always thought of groups of humans forming a less tightly bound, but the tribe or the nation or the religion as being a larger body.
Right, like a social structure.
Yeah.
And some might argue that the internet becomes a social medium which is built on top of electricity. Right? So if you're watching electricity, you just see more sparks going by. But in fact, it's now being used for the social organization, which is far more important.
The important part being the social organization where the human is the stuff.
Well, there's the question. Is evolution implemented as a pyramid in that you have lots of things in slow time down here, and then the innovations get interesting and faster, right? Because, as I said, you're only building this on top of 1 billion humans for 1,000 years, right? Whatever human history is, it's not going to last 1 million years, right? We're a very small whatever. So you have to claim that all of reality, all of history is funneling itself down to an important point, which a lot of science fiction writers...
There's a lot of evidence that the mammalian brain, if you can use a triune model, rough triune model, was the thing that allows coherence of the pack, of the tribe.
Sure.
So then, I guess I'm just lobbying for that there are bigger bodies than just animals.
Yeah, I'd actually pitch it in a different way.
Mammalian. Yeah, I mean, for example, ants, insects, certain types of insects like ants have that. And arguably, plants communicate via chemical signaling.
I didn't say it was the only. I said might argue that it's the most advanced.
If I'm right, regardless of whether the fate of humanity is happy or not, it's a flash. Okay? As far as the bacteria or any long-lived or evolutionary stable strategy is concerned, something happened up there like lightning, and then was gone, and we were back to whatever we were doing. Now maybe that turned the atmosphere into completely reducing atmosphere when the flash happened, right, or something else. But I don't know. We're too volatile to be a long-term stable whatever.
Well, we don't really know that. I mean, we can't predict the outcome of something.
We'll know by the end of our life. I actually have a totally different point. When you're talking about these different levels, you're actually modeling very different phenomena. For example, at the atomic level, you're really doing quantum mechanics.
That's right.
Whereas higher up, when you go to several zeros later, you're doing statistical mechanics. And the phenomena, the reason why you have deterministic phenomena as opposed to the quantum mechanical stuff is that you have several zeros in there, several orders of magnitude, so that things average out.
Yes.
And that's the kind of phenomena we're looking at. Similarly, you're sometimes doing modeling of humans, and you talk about how people interact, but when you do things at the planetary level, the interesting phenomena may be totally different. For example, when plants were running the planet, we switched from a carbon dioxide to an oxygen-based environment, and when people are running the planet, we're throwing the carbon dioxide back up there in the atmosphere, and we have global warming.
One of the things that did appear as front headline news for years on the Bacterial Daily was the ones who were using ultraviolet light to eat as good, responsible citizens. And then there were these other guys who had figured out chlorophyll, which was high-tech toxic stuff. And the bacteria were saying, you lose, you're going to kill us all, right? You're producing poison. You've got smokestacks, and you're sending out poisonous oxygen, and they were right. It killed them all. We like it. We came by afterwards and made use of that. Maybe something comes back by afterwards and makes use of our output.
Well, we're producing carbon dioxide, which is this greenhouse effect, which is changing the environment of the planet in some other direction.
Right, but the chlorophyll revolution, I suspect, was very quick because it's so much more efficient.
Very quick is millions of years.
Yeah.
Humans, on the course of the next 1,000 years, the warming caused by carbon dioxide emissions and all these other things destroying the ozone layer may have various other effects on the planet that on the geological time scale you're talking about with chlorophyll may actually be very small.
But as I said, a lightning flash as far as anything that's watching is concerned. I don't worry actually too much about the carbon in the atmosphere because we put more than 50% of it in already. I mean, there isn't that much more to do. It's horrific, but there's only about, what's in there now, there's only about another 40% to go because we put all the stuff there is into the atmosphere. Anyway, enough of that grim speculation. Okay, so how many levels are we built on? And how many levels are we built on? And there's some argument about it, right? There's that atomic stuff, there's chemical tinker toy. On top of the tinker toy, there are functional units, which are little machines that make use of whatever the tinker toy gives them, and then turn into something that's actually useful, like enzymes. And then you build cells out of that, and what's useful about a cell is it keeps its own inventory, as opposed to a soup. And then a tissue or organ, which is something that has a specific use. And then maybe this one organ called the brain, which does something particular, which is, again, quantum level strange.
But you also have one level above that, which is essentially climate changes on the planet.
Well,
no, I would go back to the point I made earlier that you have the nation or you have the tribe. You have competition among nations right now.
I guess I'm just not as impressed. Looking at that from a bug's eye view, I'm just not impressed by all of that.
Well, what about the ant colony versus an individual ant?
Right. Now that's a clearly viable long-term strategy, and they have not hosed the planet. Though, if the termites that ravage Africa, once every 20 years, because they're so efficient at doing that, I could imagine that might, demonstrate non-viability because they're too good. If we watch that for another million years, I don't know how long has that sort of plague group been around. I don't know.
If the computer is thinking, okay, there's an activity that's taking place. The activity doesn't comprise any particular mass. It doesn't have a level. It may be like quantum, like everywhere or numerous places at once. But it doesn't. But it's not a. I don't feel. It doesn't. It's not a level, but it's there everywhere, like omnipresent.
You're a plant. I definitely agree. The simulations we do have no mass, have no weight to them. For example, in Core War, if you want to replicate yourself, you just copy some instructions over there. There's no conservation of anything going on there, right? The computer...
Energy.
But instructions, the only thing is the conservation. You only have a limited number of instructions.
No, you can write them anywhere you like.
No,
you are using energy,
though. Cycles, instruction cycles.
Oh, yes, that's right. And it seems like that's not enough. It seems like that's not sufficient, or at least at the scales we've got. I'm happy to go on as long as you like, but I might want to get to the... This seemed to be the introduction. Ah, well. Okay. So, what I was interested in working on is the lowest level that I think is still interesting. For me, that's the functional level, because I don't understand chemistry, so how can it be interesting? I'm interested in biology. I'm interested in how things came out of what looks like tinker toy. So I'm going to attempt to emulate the physics level that starts with the function. In other words, you put the tinker toy together, you got an amino acid, and now those amino acids are little elemental objects that I'm going to try to build a system out of. I'm at this low level because that's the one I think I've got the only hope for. Anything on top of that wants even more computation. So, can 9 zeros plus however much my brain gives me plus 1 gigabyte of memory get me up a level in that domain? No. Go home. That's a joke.
So we're not considering like worms who have a lot fewer neurons being intelligent?
oh, I consider intelligence hopeless. I'm just looking for to get a good enzyme out of it. I'm not looking at the level above that. I think that's even scary.
I brought up the word because you seem to be talking about neurons there.
Huh? Oh, brain? That's my brain. Is my brain capable of combining with the limited speed of a computer I've got to implement something low level? And you're right, there is a domain confusion between the person implementing who has a brain and the computer who has a brain and the thing it's simulating which has a brain. There's several different kinds going on. So, what else could we use this for, assuming I don't get to pop up a level? Well, it can answer how soon. It can show you what are interesting pathways and tricks. It can help you with programming language research. It can give you actual biological insights. And it can help you answer the question, what's intelligence worth? And I'll put in some notions of how it can do that at the end. And you can play with it. If you can play Core War, you can play Battle Scum. The name of the system is Scum. And I think that'll be interesting. Building machines on this level, I think, well, we'll see. And it will give you someone to talk to. So, first I have to give you the nickel tour of soup. I'm going to have to start going through this faster. How long are we?
Yeah, I think about 10, max 15.
Okay.
Yeah. Well, we can have like a Q&A session at the end.
And I'm hosed again. Okay. Using my parallel to the way physical chemicals are done, which is things smash into each other, and that causes little hingy enzymes to grab things and smash other chemicals together. I'm going to try to design a system that looks like that. So, I'm going to parallel soup in that I'm going to have a conservation of whatever stuff I put into the system. And I'm going to have an encounter process of things running into other things. Except my structural elements are going to be programmatic because I'm using a computer. And instead of combining into physical trees, they're going to combine into expression trees. And what it's going to mean for one thing to bump another is the program executes. And whenever something bumps into me, just like in the real world, I get to chew on it. When you're an enzyme and something bumps into you, you get to grab it and twist it and do whatever you want with it. And the choice of language, therefore, what these elemental units are going to be is critical. And why is it always Lisp?
Why do you ask that question? There are a lot of other languages. Perl and Python are pretty widely, I mean, the question these days is why is everyone transitioning to using script-like languages like Perl and Python? But there are lots of other interesting languages. Java is pretty popular these days, for example.
I'll quote Mr. Graham.
Paul Graham.
A popular recipe for new programming languages in the last 20 years has been to take C and add some element of Lisp to it piecemeal, like runtime typing, or interpretation, or garbage collection. Have I covered all the languages you mentioned?
No.
Which one?
Closures and all sorts of other stuff.
And it's a lot more complicated than that. Perl and Python are pretty different.
Python is C with an interpreter on top of it and object-oriented. Yeah, I know. I'm manufacturing wildly. I would argue that Lisp is more fundamental than these, and in order to make that argument, I'm going to give a nickel tour of Lisp and how Lisp is derived.
Why not Scheme?
What?
Why not say Scheme?
I think Scheme is even better than Lisp, and my Lisp is going to be so crappy and cut down, it's going to make Scheme look like God. Let's make the simplest language we can. Well, what do we need? And then we can build everything up from there. So, what do we need? Well, you may know from computer science, all you need is a loop and a condition, and you're fine. Or, I'm told that the single machine language instruction you need is called decrement and branch at 0. You could build an entire machine out of that one. Or, as was observed earlier here, you
NANDiverse.
can build a universe out of NAND gates, and
Yep.
they will also do everything. You get a quantum level of increase in size from here down to here.
Actually, if you want to really get simpler, you can go down. You don't have to semantics. There's a Turing language.
You understand that you're volunteering to help me write this system. This is all a sticky trap. Oh, I didn't mention to begin with that this talk is a theoretical talk, which is Latin, you may know, for I have no results. I am currently implementing in Java, I'm looking for assistance to find bugs, holes, and things like, and routines and libraries.
So if it evolves, it'll find some of your bugs for you.
That is the theory. Carl Sims's work, which did physics modeling, his creatures were excellent at finding the holes in his physics model. They would find a way to pound the ground so that something would a zero would wrap around and they would fly up 40 feet. Because it was a really good thing to exploit. And so, bit by bit, they debugged his physics model. So, I have to agree there. Okay, so that's all we need, right? We just need one of these sets. Well, and we need some kind of syntax in which to express it, like an if-then, and then we probably need functions if we're not going to go crazy, and that wants statement terminators and parentheses. Oh yeah, and if we have an if, then we're going to have to put an expression in it, and if we're going to have expressions, we're going to need operators inside those, and for operators, we need something they're operating on, like literals and variables. And if we've got variables, we need to have a memory store. Put the variables in. Oh, if you've got NAND gates, then you need, your memory store is huge. That's all you've got to operate on. And of course, that's not just interpreted, that's compiled, so we need a compiler. And the compiler implies a von Neumann architecture on which the compiler compiles into. You need some kind of operating system that runs it, a program editor, blah, 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 blah. So, we started out trying to make something simple and ran into quite a pile.
One of the most interesting problems at the moment is how to program for quantum computers, which is a classical example of non-public.
Clearly, that can be used to implement the universe because it did.
That's right.
So I would say that that would be a good test platform.
There's someone at Harvard working on that, actually, evolving programs for quantum computers.
So let's throw that away and start over and really be honest about the simplest system. What do we mean by simplest? Well, you're only going to have one kind or the least number of kinds of any given thing, right? So if you have if you can get away with one statement instead of two, you're going to have one. Okay? And then you're going to add to that just enough concessions for your own sanity. Okay? So, the data type, let's make it words. All you get is words. Your data structure is a sequence of words. Now, of course, if the data structure is going to be interesting besides just one long list, then it's also going to be able to contain sequences of sequences. And if you need that, then you're going to have to be able to put parentheses around some of them to group which one is a list of lists, and so forth. Now we need variables. They're going to be words. You're going to need functions. They're going to be words. On account of, since I already have this thing, and it can be used for that, I'm not allowed to invent something new. Code. A sequence of words. In other words, a data structure. So your data structure and your code is going to be the same thing. If you do that, though, you will need a calling convention, which, and so the one we're choosing here is that if you have a list, the first thing in the list is the function, and the rest of them are the arguments to be passed to the function.
Perhaps you should define word a little bit better. Is that a particular number of bits?
I have no idea. I'm calling a word as we think of it. Fred is a word.
I would go numeric.
It's a symbol. How's a symbol for you? Okay. It's a thing which is distinct from a bunch of other things, and that's all I have to really say about
Can
it.
it be a composite thing?
A what?
Composite.
No, it can't be a composite thing. The only thing you get are simple symbols and a sequence. If you want a composite thing, you have to build it out of simple things by making a sequence of it.
So, for example, bit could be a word.
The word bit, or the concept of bit?
The concept of bit. For example, a single binary decision.
Well, let's see. You could make the concept of a bit by making a list of length 0, which would be false, and a list of length 1, which would be true. And then you would define a data type, which was that thing. Okay, now, of course, since code and data look exactly the same, we have to be able to distinguish one from the other. So how are we going to do that? Do we mark each of them? No, because we could get away with marking one. So which one of the two should we mark? You have to mark the data. If you mark the other one, the interpretation doesn't work. So anything you get handed as an expression is automatically something that you run, unless you run into some special marker which says this part isn't an expression, it's some data. Don't execute that part. So, what are the basic words I'm going to define? What?
Looks like Lisp to me.
Oh gosh! But this is the logic behind why that language is the way it is. It can't be any other way. So, this guy McCarthy, in this paper in 1960, says, define the following 7. Okay? Why the following 7? Well, never mind. They are, if you've got a list, something that takes the first object off it and hands it back to you, a function that takes the rest off the list and hands it back to you, and then something that does the opposite of those two, which takes one object and pushes it onto the front of some other list.
Otherwise known as cons.
Right. Otherwise known as car, cooter, and cons. But I gave them names that make sense. In order to separate data from code, we're going to invent quote, which we abbreviate as that one over there. Okay, so basically any time you put a quote in front of something, it says, don't evaluate this, it's data. Otherwise, evaluate it.
Why do that?
What?
Why do that?
Because otherwise, there's no such thing as data. Everything will evaluate down to the bottom.
Sounds interesting.
Except you end up with no data. You can only evaluate on the empty list.
All right.
This has been philosophically contemplated, yes.
That's 5.
What? Okay, sorry.
Oh. Yeah, you should probably skip ahead past some of the list stuff.
I'd say so. Anyway, that is the basic description of how Lisp got constructed. Okay, so the list I'm designing wants to have the minimum number of primitives it can, given that I fit all of these into it. Well, these take different numbers of arguments, so I can fold them together and fit them into 4 primitives. And here's my language. I fit them into 4 primitives by saying the different number, if it takes 0, 1, or 2 arguments, it does different things. Okay, so there's only going to be 4 kinds of particles wandering around in the universe, but if they get given different amounts of arguments, they're going to do different things. So, here they are. You can find McCarthy 7 up there, and then there are a few others that are useful. So, if you get handed 0 arguments, the things it does is, this one will return a pointer to the top of your tree, your object, whatever you are. This one will return a pointer to the top of whatever you ran into. This one will return the value of what was computed most recently, basically a register. And this one will return null, nothing. This is left, right, and up, which are essentially the navigational things like first and rest. And this is quote. And then we have if and if not. And then we have something that can set variables. And then something that compares things, compares whether things are equal. This doesn't compare whole tree structures, just individual things. If we want to compare a tree structure, we're going to have to build it ourselves. Set.
Is that like what some people call eq as opposed to equal?
For example, yes. It's not even equal, actually. The set is going to actually modify structure. When we say set this to this, that means whatever this thing is that I'm pointing to, take it and put it there. Because we're editing a conserved structure. Let's test this thing to see if it does some basic things that we expect. What's nil? Nil is just return nothing. Is something of a given type, you just say equal. Is it a singleton? You check its left and right, and if they're not there, you're happy. You have false and true, which are, as I noted, nothing and anything else. To do not, you do an if not compare. Here's and, here's or. And one thing that's particularly hard is execute A and then execute B, and obviously return whatever B was. That's fairly hard. Okay, what can you implement with this? I won't go into the rest of the system that's built around this, but the language is the important part. Well, suppose I want variables. Here's the top of my tree. Instead of putting the code at the top of my tree, I'm going to put my code over there. And I put an if, so it'll always execute, because this is going to return some true value, and so this is going to execute. But what this is over here is a variable store. Okay? So it's just some tree structure that goes down this way and hangs off of every one, whatever I want to store. One variable, two variable, and so forth. How do I access them? I take myself, which is the pointer to my top. I take the left of that, which is here, and then I do however many lefts I need to get to my variable, and then I take a right, which takes that variable, and that returns me the value. And so that's recall. That's recall above, and then you have a store and a clear.
I want to say something quickly about the brittleness or the robustness of a system like this. I mean, it seems like a lot of the really, really simple, fundamental things. I realize you don't want to cheat and just give them away, but it seems like a lot of really fundamental things here take a lot of instructions, which is not a big deal, but also it seems that they're pretty brittle and that
they're hard to find.
That they're hard to find, and then once you find them, very simple changes might tear the whole house down completely.
I agree.
I'm not necessarily sure that making something robust and cheating are the same thing. I mean, you can make a...
Oh, it's not cheating, but he's saying in my quest not to cheat. Am I doing something that's too low level? It's never going to go anywhere.
Well, I wouldn't even say low level. I don't think low level. I mean, you could go as low level as like NAND gates, but I think that what he's getting at is the representation being robust in the sense of being, you can fiddle with things and it won't break the entire system.
On the slides that went by, one of them was, this is robust in that everything means something and nothing crashes.
I see. Yeah, that's true. That'll at least get you basic robustness.
There's no specific syntax. These things are actually surprisingly robust in doing whatever they do. And I would expect for a long, long time the way they do things to be inefficient. Right? They do the same thing 3 times, for example. Or they check a thing and then they check the thing again and then they do the whatever. Right? You would only expect the perfect version, which you're thinking of, to evolve over a long period of time when things knock out pieces of it that were irrelevant. And it turned out to be a little faster. I would expect the first thing that figures out how to match 2 structures to be quite ugly and quite slow. But a lot better than anybody who can't do it.
We have some slides covered the biological specification.
The biological specification is what? The specifications are that in place of amino acids, I'm using these 4 basic primitives. They bump together into trees just like amino acids do bump together. We know that aminos can be generated chemically, not biologically, so they exist in nature. When they bump together into something like this, we're basically considering it an enzyme, something hingy that acts. And then we basically are picking 2 objects out of the soup and saying, you ran into you, we run this one, and we say you can chew on this one. And so then we just pick arbitrary sets of them out of the soup in the same way that they would actually be operated. There isn't one. It's replicating things that are capable of generating more of itself will be selected for. What?
Well, it's kind of an implied objective function.
It's the universal implicit one.
Yeah.
We're running out of the last minute or two, so.
Right. Okay.
Yeah.
So here are data structures like structs and arrays. They're not very complicated. And here are various machines. If you can give me just a little more time, but all right. what you basically do is you keep two quote pointers lying around which point into two structures, and you just walk down the trees and do equals between each one of those nodes. Now, since you can't iterate, this thing has to be hit a bunch of times, once for every node. That seems like it runs really slow. Unfortunately, in reality, that's the way we really are implementing. Then there's digestion, which is I ran into something and I want to chew it up into pieces because I'll need the pieces to construct something. Basically, I keep a pointer into whatever I'm eating currently, and I take the pieces and put them into my store, which is just a linked list of each kind of object. And then finally, a structure duplicate, which is I have a pointer into something I'm duplicating, and I use my store to construct another one by traversing a similar tree. And the question is there a way to do iteration with this system? I've come up with several, but they're both fairly evil, and you might want to come up with ways of disallowing them. They're things like you start executing here, and then you take the piece of code that was above you and just put it underneath, and then it executes down here, and then you take that piece of code and put it under there, and it continues executing. That seems like a hack somehow, but something might find it.
Oh, things will find all kinds of interesting hacks.
That's the issue.
Well, it's kind of what you want.
Right. So, machines that might be, useful machines that might get built. I'm almost done. Things can attach to you and stay hooked onto you and use you. If you're in a population that you're the metabolism, you might want phages that run around and find things that are hooked to me and kill them. So it's going to have to do a pattern match on whatever is hooked to me and then grab it and eat it, which is what white blood cells do. And then you could have a matcher and a duplicator, something that finds a particular structure and then makes another one of it. That's also known as reproduction. If I get that far, you'll hear me gibbering from wherever you are. That would be a happy vindication of the system.
You'd be surprised what you can get random reproduction in.
If I get something that reliably generates itself, I'll be very happy with it. So just very quickly, the design of the system is I implement these things in this language, and then I rain down on top of it lots of extra resources because you need to keep inputting into the system. And then these objects just float around and run into things, originally just atoms, and they have a chance to glom together, they have a chance to be hit by a cosmic ray and changed, and so forth. Basically the same functions that happen.
What do you start with?
Just the 4 primitive types.
No, I mean in terms of configurations in your pool.
The 4 primitive...
The things that bump into each other and chew on each other.
4 primitive atoms.
So
singular, basically they are one atom molecules.
And you think that's enough to get started?
Well, one of the things that can happen is when 2 things strike into each other, they just stick. That's in the same way that in the real chemical soup, before anybody gets good at enzyming anything, the way everything gets combined together is it happens to just form a chemical bond. And so that's one of the things that can happen. Let me just run through these and see if there's any... The question is, what would you display in such a system? All you really get are histograms of interesting things going on. What you'd want to watch for is discontinuities. Suddenly you get a shoot-up of this kind of thing, or you get a molecule which is very big, statistically unlikely, and yet you're getting a lot of them. And then there's the question of efficiency tricks. And here's where the question of what a brain is worth. If you implement the system at first, and then you implement it later on, faster, you can see, if your brain gave you a factor of 1,000,000, then it's worth 6 zeros in this domain. You can also pre-compile most atoms, most molecules don't do anything. You can have a concept of sugar, which makes things operate faster. So what's this of use for? Last couple of slides. Well, it's a demonstration project for abiogenesis if it in fact generates anything that can reproduce itself. Something alive, and self-capable came from something that wasn't. And assuming determinism is true, it would prove a pathway for us, because once you start out on this sort of thing, you can see that a chain of many levels might. If determinism isn't true, and we are not in fact mechanical inside, then no simulation is going to implement us.
You were talking about this the other day.
What?
It's beyond the scope of this single slide. I think that's
Yeah.
Philosophical statement. We may not, in fact, if you have a soul, you ain't going to implement you in a computer.
How about Schrodinger's cat?
You'll be able to implement Schrodinger's cat. This would inform actual biology in that you could do experiments on it. In other words, you could have 1 million generations fast, whereas fruit flies are expensive. This is why Evita got implemented in the first place, so that he could run generations faster. How is this of use to A-life? Well, it's kind of a grail to get a single system that goes from computation through reproduction. It can tell us what's doable and when, and besides watching how well I can implement the system, I can try coding a functionality like struct match, and then run the system and see how long it takes it to get to struct match. Well, that's how much I took versus how much it took is the ratio I provide of intelligence provided to that particular functionality. And finally, I could use assistance. I need to find holes in the language. There must be some. I found some that would make the thing totally not work, and I patched them, and now it seems fine. So if I find another one, I'll be disappointed, right, when it totally doesn't work. So I'm looking for interesting features and tricks you can do with this, like creating variables and such. And I would like to play some games like Martin proposed with battle machines, where we construct little devices, you make a population full, I put my soup in your soup, and we see who eats each other. Efficiency tricks for the system. A factor of 1 million isn't nearly enough. As we noted, I need 10 to 20 zeros out of the thing before something interesting happens. And finally, because these things run long, and because we never actually get to chat as opposed to a presentation as long as we want, I would like to try to put together a group of us sitting down, not having a presentation, but yet having a topic of discussion. I'd like to propose it for 2 Mondays after this one. In other words, the 2 Mondays that's in between this one. Do you guys typically have the Monday slot free?
Well, we were talking actually about setting it up for a Tuesday for people who can't do it on a Monday.
Oh. Okay.
And just getting together at a, just getting together someplace for a social meeting. So we were actually talking about that.
All right. Well, I was saying Monday because I know at least that people are likely to be.
Right.
All right. Hands. Who's free on what is that? The third Monday? The third Mondays. Obviously, you don't have to be sure, but thank you. No one is free.
I think so.
Comparatively, Tuesdays. Is the next Tuesday better?
Yeah.
Okay. Thank you. They're about equal. And then finally, the whole point of doing this work was not because I was intrepid and fascinated. It was to introduce myself so I could put up the fact that I am always looking for nonprofit PC work, or you could hire me to do evolution. But if you want me to get the sucker implemented, I'm looking for contracting work in this field. So that's it. Thank you. I'm sorry I ran over. How much questions we got? Much or not?
I think maybe just casual.
Yeah.
Okay.
I actually had a bunch of comments. I was kind of saving them up toward the end because I wanted to make sure you could get through the whole thing. But one comment, just from the beginning, you mentioned that systems like Evita, you said they kind of cheat in the sense that they have instructions that replicate these. That's actually not really true. I mean, if you look at their instruction sets, if you look at something like Evita or what's the other one? Tierra, Nanopon, and stuff like that. They don't really have an instruction that just says copy. They actually have to do, self-assembly over to another memory location.
I said some of them have replicate me. I don't think I said Evita particularly. Did I say Evita particularly?
Well, the way you said it kind of implied that all of them did. And
they have things like that. Some of Evita's instructions strike me as bigger than others.
That's definitely true. That is definitely true. But you could also say that of a LISP system, that some of the instructions are...
I don't think you can say that of my 4 particles. You're right, I may have doomed the system. But
like I've thought about doing things like NAND gates, that sort of thing, to experiment with ultra-primitive sort of things. But my point was just that they don't necessarily just have an instruction that just copies.
You're certainly right.
And the other point was not saying that this is like a bad direction to go in or anything, but it seems like it has been demonstrated, like for example, this has been done with Vita, I did it with Nanopond, it's been done with a bunch of different things. It's been demonstrated that you can generate random sequences of instructions and get self-replication that way. Those instructions, however, are a little bit higher order than what you might be talking about.
They are higher order, and I'm claiming that they are not a uniform order.
I'm not so sure that physics is uniform, though. I mean, if you look at, particle physics, you have all these weird particles that do all kinds of strange things when they interact. I don't know if... it seems like, in the history of science, we expect our universe to be rational and uniform, and when we really dig down into physics, we find that, and we have someone here that knows more about physics than I do, but we find that it's not necessarily like that. We find this particle zoo, and we find all these strange things like... well, we think that.
I think maybe we should move this one offline.
It's long, but see if anyone else has any questions.
So I'd like to just thank Paul for coming tonight. Remind everybody, so the first Monday in May will be our next presentation on soft robots, and just again like to say thanks.